In late 2022, generative AI suddenly went mainstream. Millions of people started interacting with language models like ChatGPT, and within months, Microsoft, Google, Amazon, and Meta began pouring billions of dollars into scaling up their own AI infrastructure. But building, or training, sophisticated AI models requires an enormous amount of physical computing power. It involves processing massive quantities of data and performing vast numbers of mathematical calculations. It is a heavy physical lift, not just a software puzzle. This diagram shows a traditional computer processor, or CPU. CPUs are engineered to execute complex tasks sequentially, solving one problem after another. When you force massive amounts of AI data through that single pathway, it creates a severe traffic jam. The technology industry quickly realized the exact machinery needed to clear this bottleneck already existed. It was sitting on the shelf, originally engineered for a completely different purpose. NVIDIA provided the foundational hardware driving this leap in computing power, a company that had spent the previous 30 years building technology for video game graphics. In 1993, Jensen Huang and his co-founders started NVIDIA with a very specific goal. They wanted to transform personal computer graphics. At the time, personal computers were getting more capable, but rendering sophisticated three-dimensional graphics required a massive amount of computation. Existing processors struggled to handle that kind of specialized workload. NVIDIA solved this by designing hardware dedicated entirely to graphics rendering. In 1999, they officially introduced the term GPU, short for Graphics Processing Unit. This diagram shows how a GPU operates using a concept called parallel processing. Instead of a processor performing calculations in a sequential line, this parallel architecture allows the processor to perform thousands of simple, similar mathematical equations at the exact same time. By figuring out how to efficiently render the complex geometry of 3D video games, NVIDIA had inadvertently created a highly efficient computing architecture. In 2006, NVIDIA made a critical decision. They introduced CUDA, a software layer that allowed developers to program GPUs for calculations far beyond traditional graphics. Suddenly, scientists and researchers could take hardware originally meant to run video games and use it for complex simulations and heavy scientific computing. This created what economists call a network effect. As developers spent years building applications using CUDA, they locked themselves into the NVIDIA ecosystem. The more tools built for the platform, the more valuable the physical hardware became. By investing heavily in that software layer, NVIDIA turned what could have been a highly replaceable piece of hardware into a technological platform the industry relies on completely. Then came 2012. Researchers working on a deep learning project called AlexNet were trying to teach complex neural networks how to recognize objects in images. It turned out that crunching the massive data sets required to train those neural networks relies on the exact same parallel mathematical calculations as rendering millions of tiny polygons for a video game. AI researchers co-opted decades of gamer-funded parallel processing technology simply because NVIDIA had made that hardware programmable. NVIDIA's recent financials show an explosive upward spike, culminating in a record $215.9 billion in total revenue for fiscal 2026. Breaking that total down, $193.7 billion, the vast majority of their income, is generated solely by their data center business. These immense sales figures don't look like individual consumer graphics cards sitting on a desk. They are massive AI factories, sprawling data centers filled with tightly networked computing clusters. NVIDIA now serves as the heavy machinery supplier for the global intelligence economy, operating at a scale far beyond its consumer roots in electronics. But that dominant market position relies heavily on an external global supply chain. NVIDIA designs the chips, but they depend on a complicated network of manufacturers heavily centered in Taiwan. The actual fabrication of advanced semiconductors involves specialized high-precision manufacturing that creates a rigid physical bottleneck, exposing the company to global geographical and political tensions. At the same time, the world's largest technology companies, Google is developing custom silicon, Amazon is building its own chips, and Microsoft is doing the same, all to reduce their reliance on any single supplier. The companies that define technological revolutions rarely do so by predicting the exact consumer application everyone will eventually use.
Instead, they do it by spending decades meticulously building the underlying infrastructure that makes those future ideas possible.